Okay, let's continue on chapter 21. Now let's go to continuous charge distribution. So far, remember when we have a magnetic field, electric field for a positive charge, right? For example, this one charge right at this point P, right? We found that this is the electric field, and the electric field is equals to KQ, correct? This charge Q divided by r squared, right, in that direction, right, r hat. Okay, this is the case when we have only point charges. What happens if we have a distribution like this one? Okay, a distribution. Well, we're looking for the point, have a charge right here, Q, have a point right here. How we can find the electric field? Well, we use the same technique. So we use a element of charge right here, dq, correct, in this direction. And it's gonna be the electric field at that point P. Okay, the same thing, right? We have this is the unit vector. And now let's go back to the electric field. In this case, the electric field, right, at this point, done by this element of particle, right, infinitesimal particle, is equals to K dq over r squared, correct, in that direction. And that's the formula that we use for each of these element of charges right here. Later, to have the whole thing, right, have to the integral, right? So the electric field is equals to K, right, times the integral dq over r squared, correct? R hat. So these are the equations that we are supposed to use when we have distribution, or to use the integrals. Let's do it. So the electric field, correct, is equals to K dq over r squared. Perfect. Perfect. Correct. Great. R hat. Also, the electric field is equals to K times the integral, right, of these quantities. Perfect. Okay. R squared, right, R hat. Now let's apply these conditions to some distributions. Let's do it. Imagine that we have this charged rod, right? This one right here. Perfect. The charge is Q, correct? We have a length L. We're looking for the electric field at that point. Imagine we're in the x direction. Okay, so the electric field right here. Perfect, point P. Now imagine this is the charge, correct? The same thing as before, what we're looking for this infinitesimal charge, right, dq, correct? Imagine the distance from here to here is a, and the distance from here to here is gonna be x. Again, we are in the x direction. And this is gonna be the x, this segment. Okay, now let's find the electric field at this point, correct? This is the electric field produced by this charge, infinitesimal charge. Let's do it. So we have the electric field is equals to K, right, times the integral of the charge dq over r squared. Let's find only the magnitude. But when we're dealing with distributions, it's easier, it's better to use densities. For example, we have three types of densities, right? We have linear density, surface density, and volume density. This is for the charges is defined as the charge divided by L. This is the charge divided by area, and this is the charge divided by the volume. Now, using in this case the infinitesimal charges, this is the same as dq over dx, and this picture of dl equals to dq over dA is equals to dq over dV. Okay, so depends on the distribution. Is linear, is surface, or volume distribution is gonna be the relationship. Okay, for this case we're dealing with lambda, okay, because linear distribution. So in this case we have that dq is equals to lambda dx, correct? So that we have is equals to k integral of lambda dx over what is the direction from here to, what is the distance, or right, it's gonna be in the x direction, x squared. Okay, perfect. And then the electric field is equals to, let's do it, gonna be k lambda, correct, linear of the x over x squared. From where to where? From going to this point, gonna be the distance a, and a plus l. Okay, so this equals to k lambda, correct, times 1 over x from 0 to l. L plus a plus l. A plus l. Also, it's from a, but a is this unit. Okay, perfect. And what do we have at the end? That the electric field is equals to k lambda, correct, times 1 over a minus 1 over a plus l, correct, and this is equals to what? K lambda over a plus l, correct, times l. Great. Now let's go back to lambda. Remember, lambda is gonna be q over l, so it's gonna be electric field is equals to k lambda is gonna be what? Q over l, correct, times what? Times l over a plus l. And what do we get then? Okay, so from here we have that the electric field for this distribution is equals to k q, correct, over a plus l. Also, we can use the conversion of k, right? Using remember, k also is represented 1 over 4 pi epsilon naught. Okay, perfect. It's gonna be 4 pi epsilon naught, correct? Epsilon naught times a plus l. Right? And that distribution for this particular case. Now let's go to another one. Let's go to a ring. Okay, hurry. Let's go to a ring. And the technique is the same, right? We're looking for an element of the charge, one, and then use the integral for the rest of the distribution. Okay, one more time. This is again a ring. Imagine that's the ring, and we're looking for the electric field at that point. The same thing, right? Let's take an element of the charge right here, right? The q, the total charge is q, correct? And the segment, right, of the length is the s, because we're dealing with arcs, correct? Let's take this distance to be a, the radius, the distance to be x, correct? And this distance again gonna be r. And what do we have? Well, we have that this is my electric field at that point. But in this case, we are interested on the x direction, right? If this is theta and this is theta, correct? We have that, for example, r, the square is equals to a squared plus x squared, right? Plus x squared. Also, cosine theta is equals to, because we're looking again for this component in the x direction. Also, we can find the y direction. By the y direction, then it is 0. They cancel each other. Okay, perfect. Only in the x direction we have a net electric field. Let's do it. Again, because these are related in this way, gonna be dE, right? What else? It's not dE, right? This is gonna be equals to, let's use this part, it's gonna be a over, no, it's x, right? It's x, x and r, right? X over r. Perfect. Right, now we're dealing with this component one more time. In the direction of the dE, right, cosine theta. Perfect. And what is dE? Well, it's coming from this equation right here, gonna be k, right, dq divided by r squared, correct, times cosine theta, but cosine theta is x over r. Perfect. And then this is equals to k dq, right, x, okay, kx, okay, divided by r cubed. One more time, this is a linear distribution, so let's use this density, right? So gonna be then dq, the same thing as before. We have the component of this electric field is equals to the E is gonna be what kx, what is dq is gonna be lambda times what, times in this case the s, right? The s is the element, okay, divided by r cubed. Okay, when we do the integral, what do we have? I need more room. So okay, let me try to do right here. The electric field in the x direction is equals to kx lambda over r cubed times what? Times the integral of the s. But the s goes from 0 right to the total length. What is the total length? The circumference gonna be 2 pi r, but r is the radius. In this case, the radius is a. Gonna be 2 pi a. Correct. And what is this? Is equals to again? Okay, kx lambda over r cubed. Correct, times 2 pi a. Perfect. Now we can substitute lambda. Correct. And what is lambda from here? One more time, it's gonna be q over l. But l is the total distance, right? The total length. It's gonna be 2 pi a again. Correct. So it's equals to, one more time, equals to kx, right? What is lambda over r cubed, right? What is lambda? Lambda is gonna be charge over 2 pi a, right? The total length. Perfect. Times 2 pi a. And this is equals to kx q divided by r cubed. Got it? And this is the electric field at this point produced by this distribution. Of course, you can work with R, right? Using these quantities like also with K. You can say K gonna be Qx over 4 pi epsilon naught. And what is R? R is gonna be what? I raised it, but gonna be a squared plus x squared, right, to the 3 halves. Okay, so the answer is the same. Perfect. Now let's go to the next distribution. Now let's use a disk. It's similar to this one. Okay, but what about in that y direction? Well, we take another element right here, right? So we have again the component. This is, let's say 1, and this is, let's say 0.2, correct? But we break this into components, one in x direction, one in the y direction. The same thing for this one, right? One in the x and one in the y. But these two are opposite in the same magnitude by symmetry, right? By the symmetry right here. Well, they cancel out. We have only electric field in the x direction. Okay, perfect. Now let's go to a disk. For a disk, and let's find the electric field using the same technique, right? Similarly to the ring. Now we have a disk, right? Well, let's use it the same way as for the ring, correct? So the disk, again the same charge Q, and we take an element, right, of surface. It's gonna be my dA, and again we're looking for the electric field in the x direction, similar to this one. In the y direction they cancel out, right? Only in the x direction, correct? In the x direction, correct? In the x direction, in the x direction only. Okay, the same thing as before. Now this is my dA, but what should be the A in this case? Well, again, let's try to cut this part and make a line, right? Then we have this area right here. This is also, let's label this. Remember, this was A, right here. Now let's label this Y, right? Y, and let's label this thickness dy. So what should be then? Well, let's take this point right in the same way as before, and this is the electric field produced by this let's say ring. Okay, perfect. Or tape over here. Okay, let's do it. So gonna be dy, the thickness. What should be the length? The length is 2 pi y, correct? That's the length. Perfect. And what should be the area? dA, okay, dA is equals to 2 pi y dy. Okay, remember looking for the electric field at that point. Perfect. And now let's work for the electric field. Remember dealing with the electric field in this direction. The same thing as before, right? Gonna be this element is equals to k, right, dq, correct? By the way, this one is gonna be the same thing as before, right? It's gonna be actually, because this is the angle theta. One more time, this is r and this is x. The same thing as before. Perfect. So it's gonna be the e again cosine theta. Very similar to the ring, correct? The difference is gonna be now this is surface. And in this case, let's go back again to these equations. Q dq, correct? K dq, perfect. Oops. dq divided by r squared. In this case, r is x, right? It's gonna be x, the x direction. Okay, x squared. Perfect. Oh, well, no, it's not x, right? This is r, sorry. Okay, gonna be r squared, perfect, times cosine. What is cosine? One more time, cosine is y over, that's not y, it's x over r, right? Correct? X over r, perfect. X over r. Great. Now let's continue. Now let me erase this part. Again, now let's go back to dq, but now this q is for a surface distribution. Now let's go to sigma right here, right? This says that dq is equals to sigma dA. What is dA? Well, it's gonna be 2 pi y dy. Great. So in this case, we have that this component is equals to k over r squared times dq, but dq is equals to sigma, right, dA. Correct? So it's gonna be sigma 2 pi y dy, correct, times x over r. Perfect. And then what do we have? Let's continue right here. Hopefully we have enough room. Okay, great. So this is equals to let's arrange in this way. It's gonna be k pi sigma over r cubed. Not yet, r cubed. What else? Let me see what else do we have. Integral of 2y dy over r cubed, correct? I missed x was right here. Okay, perfect. Now one more time, what should be r? R is equals to, well, from this figure, r is equals to, look, this triangle, it's gonna be y squared plus x squared. When this is, okay, square root, right? 1/2, that's r. Let's substitute this value right here, and what do we have? So it's equals to y squared plus x squared, right? 3/2. And now let's do the integral. You can go to table, or we can do it very fast. Right here. Okay, let's try to do it. Let's use substitution. Let's take u equals to y squared plus x squared. What should be du? Gonna be 2y dy, which is the same as that one, right? So this equals then to k, right, pi sigma x integral of du over u to the 3/2. Correct, and then this is equals to k pi sigma x, correct, it's gonna be what? U to the negative 1/2, 2 divided by 1/2 negative, correct? Perfect, and then what do we have? This is equals to I need more room right here. So this electric field is equals to K pi sigma x, correct? Negative, gonna be negative right here, correct? What else? 1 over times 1 over x squared plus y squared, correct? 1/2 from where to where? I erased it. Okay, from 0 to a. Correct? From 0 to a. Perfect. And when we do the calculations, we'll get that the answer is this one. Okay, when we do substitution, right? This is equals to k 2 pi sigma, correct, times 1 minus x over the square root of x squared plus a squared. Correct? That's the integral. Perfect. Now let's see what happens when we go to some conditions. Imagine that we're looking for the case when a, right, which is the radius, is much larger than the distance to the point, right, p, x, in this case. What happened then? Well, in this case, let's see, it's gonna be then the electric field is equals to k 2 pi sigma times 1 minus, look, when we establish this condition, for these two, they become very small, becomes 0, and then becomes just a squared. Square root is gonna be then x over a. But again, because this still is much larger than x, so this becomes, right, approaches to 0. And then what do we have? This is equals to k 2 pi sigma. When we use this condition, perfect. And then, well, we can use k, remember, is equals to 2 pi sigma over 4 pi epsilon naught. And why is this? This is equals to sigma over 2 epsilon naught. Correct? Well, we represent this condition in this way. Imagine that we have a huge charge sheet, right? And we have this equation, right? Imagine this is the sheet right here. It's positive, it's infinite sheet, right? And now this is gonna be the electric field, correct? In that direction. What is the magnitude? The electric field in this direction is sigma over 2 epsilon naught. The same thing right here, right? Equals to sigma over 2 epsilon naught. Imagine that we have another one right here, correct? And now this is negative. And what should be the electric field? Well, it goes toward the plate or sheet in this case, correct, with the same magnitude, okay? Electric field equals to sigma over, imagine they have the same charge, the same density, so the same magnitude, okay? 2 epsilon naught, the same thing right here, right? The electric field is sigma over 2 epsilon naught. Perfect. What happened? We close this together. Okay. What do we have? Remember that they have the same charge distribution, but one is positive, one is negative. Great. What happens when we place this together? Well, we have this electric field in between. This is positive, this is negative, correct? So it goes from positive to negative, the electric field. And what is the torque? Is this, when we put this together, is this plus this equals to sigma over epsilon naught, right? And this is a very important conclusion because we use this for capacitors, right? It's a very important device in electronics, right? Capacitors, and we use this result in many calculations dealing with capacitors. The electric field in between is equals to the charge density divided by epsilon naught. Got it? Okay, perfect. Now let's go to the last topic for this chapter. The last topic is gonna be the dipole, right? The electric dipole. Let's do it. Electric dipole. Okay, great. This is very important. Very important conclusion. Yes. Okay, the electric dipole. Okay, electric dipole is when we have 2-point charges with the same magnitude but opposite sign. For example, we have negative right charge and positive charge, the same magnitude but opposite sign. Right, they're connected by a distance d. One more time, this is electric dipole. Correct, electric dipole. Of course, this is negative charge and this is positive charge. Now, what happens when we place this in a electric field, a constant electric field? For example, this one. Okay, it's constant. Correct? Imagine that we represent this in this way. Okay, we have this plate, huge plate, like the capacitor we found before, remember? Okay, this is positive and this is negative. This is the electric field, it's constant. Let's take this to, this is the dipole, right, and place it right here. What happens? We place it right here. Well, this is negative, right? This is negative, and this is positive, correct? The distance d. They're connected, they're dipole. Okay, well, this feels a force in this direction, this feels a force in this direction. But these forces are the same in magnitude but opposite direction. What should be the net force? 0, right? The net force is gonna be 0. Okay, what happens in the case when they are not aligned to the electric field, but they have an angle, like in this case? This is negative and this is what? Positive. Correct? That's the distance d. Well, in this case we have a torque, right? A force is applied on this charge. Positive equals to charge times the electric field, correct? And another force applied to this charge. Remember, this is positive charge and this is the negative charge. So what should be then the force for this negative charge equals to negative the charge, right, times the electric field. Correct? We have then this distance d. Now we have a torque, right? We have a torque. How do we define torque? Well, torque, remember, is tau. The symbol is tau for torque. Tau. This equals to the cross product of the lever arm times the applied force. Correct? But in this case, imagine that rotates to this, let's say, center. Let's say center on mass. Okay, perfect. So from here to here, we know that this is the sine theta, this is the angle theta. But right here is half this distance. Okay, now what should be the lever arm from here to here, right? It's gonna be equals to, because we have 2 in general, this is the general equation, we have 2, so the torque, tau is equals to torque 1 plus torque 2, right? Produced by this force and produced by this force. Okay, okay, perfect. So it's equals to what? It's equals to R times force, right? But R is equals to D divided by 2 sine theta. And what is the force? The force is the charge times the electric field plus the other torque, right? They go in the same direction, okay? So this is equals to D divided by 2 sine theta, correct? Times the same force, which is, correct, Q times the electric field, correct? This is the magnitude. The direction is gonna be clockwise. Remember, when we're dealing with torque, in this case, we can use this convention, right? Clockwise or counterclockwise. Perfect. This is clockwise. The direction, this is gonna be the magnitude. Great. So what should be then the torque for this dipole, electric dipole in a electric field? It's equals to the torque is equals to what else? The Q E times sine theta. Correct? Now, this is a quantity. Every time from this analysis, every time we have a vector, because electric field is a vector in sine or a vector in cosine, we use the cross product or the dot product, depends. Okay, okay, let's do it then. So it's equals to what? Let's define dq. Okay, before that, let's define dq, right, as p. Right, this is the electric dipole moment. Okay, it's equals to d times q. When we use that, so what do we have? This is equals to p, right, e sine theta. Also, we can represent this as the cross product, right? This quantity times cross this quantity, correct, to have the torque. So torque is equals to this moment, electric moment, right, cross this electric field, correct? Perfect. This is electric dipole moment, right? Electric dipole moment, P. Perfect. Now, because we have rotation, let's try to find work, right? We're making work. We're producing, the field is doing work. It's rotating, right, this electric dipole. Also, from here we can find the potential energy for this electric dipole. Let's find the potential energy involved in this electric dipole. Let's do it. When we're dealing with rotation, we found the relationship. Remember, when we're dealing with potential energy in the only one that we know so far, which is gravitational potential energy, we relate gravitational potential energy with work, right, in this way. Where again, gravitational potential is negative what? Negative mgy. Correct? Negative mgy. This is for gravity. Let's do the same thing for this electric dipole. We can do that because the force acting in doing work by gravity, the force is conservative force. The same thing happened when we're dealing with the torque. The force that is creating the torque when we're dealing with these electric dipoles, the force is conservative force. Remember, so far we have three conservative forces: the force done by gravity, the electric force, right, and the force done by the spring. Perfect. So they behave very similarly. They have the same form. Perfect. Now let's find the work again. Then when we have the rotation. Perfect. So work then, this rotation is equals to torque times d tau, d theta. But where is okay, but what is torque? Torque is equals to what? P e right sine theta. Okay, let's do it. So work is equals to tau. What tau is P e right sine theta d theta. But when we have the torque, right, because in function the angle theta, but the angle theta decreases. If the angle theta decreases, the change is negative, right? So we have then, this is the case when we have this element of work. Okay, perfect. Now let's find the torque work. Let's make the integral equals to negative PE, correct? The integral sine theta d theta. From where to where? From theta 1 to theta 2. Right, then what is this? Okay, when we do this integral, we have that this is PE right cosine theta 2 minus PE right cosine theta 1. Now I want to create something like this, right? Because this is for conservative forces. So we can create again that work done by the field, right, on this electric dipole is equals to the change on this potential energy, correct? Now let's define potential energy in the same thing as we did for gravitational potential energy. Well, taking these quantities, the potential energy for this electric dipole is equals to negative P, right, E cosine theta. Right, this, in this case, right, this is in function of y, right? It's gonna be mgy. The quantity changes is y. The same thing happens right here, right? In this case, in function of the angle theta equals to negative P, E, right, cosine theta. Correct? And this is the potential energy of an electric dipole, right? Is defined in this way. But look, right here we have that this is P cosine theta. We can also use vectors. So this is equals actually to the dot product, right, of these two vectors. And one more time, this is the potential energy of an electric dipole, right? Electric dipole is gonna be negative P, right, the dot product E. Correct? And of course, right, work is equals to negative the change in this potential energy. Right? Okay, perfect. And with this, we finish chapter 21, and I'll see you in the next chapter. Thank you. Bye.